Okay, so welcome. Today is going to be a presentation about object detection using Haar-like features. So we'll go ahead and look a little bit about the stuff that we're going to discuss today. I'm going to actually go through, if you remember before, actually I had a small presentation on Haar-like features. So we went on all the basics of the math behind it and some of those things. So I'll do just a quick recap on that, and then I'll go ahead and talk about how you actually would be able to train a detector. So today you might, actually you can use this presentation if you want to have a kind of an example on the steps that you would take to train your own detector, Haar-like feature object detector. So basically the steps goes, we have to do some data preparation at the beginning, collect some negative samples and some positive samples. We'll talk in details about that. What is negative and positive samples?
Are they balanced? The same number or different number of?
No, usually the negatives are usually in a proportion like twice as many as the positives. Or yeah, something like that. It's like they're. The thing that you will notice today is that you can use several parameters and you can change those parameters in so many different ways and combinations, and you might get different results for different stuff that you tried on different things. So I can't just say, okay, it's a rule, go ahead and do twice as many negatives as positives, but that's kind of the common thing to go with. They could be almost the same number, but they should be big numbers. So we're talking here about thousands. We're not talking about 20 images. We'll do some object marking. That is kind of one of the other essential steps. Before we create our training samples, we create our vector, and then we will look at the commands used to actually train the detector, and then look at the testing, and then I just also included some of my results on what I did with a leg detector. Basically, it's just a kind of a lower body leg area detection for kind of partially human detection. So why do people actually do object detections? Well, there are millions of applications out there. Just a couple of them right here listed. There's automatic image annotation. You can use them on search engines and online data sets to mark, those images with the keywords, saying, okay, if I have this keyword, then those images contain this object that I have just entered, and stuff like that. Video surveillance, monitoring inventory, shipping, military and security. If, for example, you want to look at one kind of pharmaceutical bottles that you are putting on some shelves, and you want to go ahead and detect those bottles. If in security you want to detect if there's some suspicious object that is present at some area, it could be like a bag, it could be anything. So it's any kind of object that you want to look at and detect it and send out an alert or anything like that. That's also very important. So these kind of like the things that you might think of when it comes to object detection. Why would we want to actually do this? So as I said, just kind of a small recap of what we did before on the Haar-like features. So basically those are the features that we're looking at, and maybe I should just go ahead and this here. So basically, as you see, those are some different combinations of Haar-like features. You can also use more than those, but basically what you're looking at is that you have your image here, and then you are looking at different sections of the image. So you have kind of a detection window that you go through the image, or you can call it even blocks over here. So basically, you're looking at that image, and what you do is that you have those features. For example, let's say the first one, like right here. So you have a dark region and a white region. So you're looking at the pixels that lay in each of those regions. And then you calculate the sum of those pixels and do the difference between the two. So for example, let's say our function fi would be the sum of all pixels in the white region minus the sum of all pixels in the black region. So it's just simple math. It's not anything fancy. And remember, one other thing is that your image is grayscale, so you're not looking at colored images or anything. So you convert that to grayscale, and you have whatever 0 to 255 values for each pixel intensity, and then you have this. And then what you basically do with this is that use that with a threshold that you set. And if this is greater than that threshold, then basically you give it a 1. If it's not, you give it a -1. That's why it's kind of called that name. So if over here it's greater than t, the threshold, over here it's less than t. So you have just 2 decisions on over here. And using those different features, you can look at not only vertical or horizontal, but also diagonal and other combinations. So you'll be looking on all those different regions to determine where it's kind of an edge detector, so you determine exactly where your features are looking at. So after you do all of those calculations, you take all of that, and you can also do what is called an integral image, which basically sums regions of all of those that we have just, all those computation that we have just done on all those pixel regions, and you can combine it in one integral image, which would make the computation much faster for you, and that would be the input for your classifier. So basically, you have your input image, you do the Haar-like features for detection region, you calculate the integral image, and then you set your cascade of classifiers, which basically, according to Viola and Jones and the paper that they had on Haar-like for face detection, so they did a cascade of weak classifiers. And by weak classifiers, we don't mean that they're weak in the sense that they're not good. They're just a little better than just saying they're just good enough, for example. So it's not a classifier that you can use on its own, but you need a combination of all those classifiers to create a stronger classifier.
What's this weak learners?
What?
What weak learners are you using?
Oh, well, we just actually took the default weak classifiers from the OpenCV library, so we didn't specify those classifiers. But actually, in the training process, by using our own samples, training samples, we set those. Okay. So basically, we start by preparing our negative samples. So what we want to do is that we want to try to find a list of many images as we.
In the previous
Yeah, sure.
slide, what's the F1, F2, F3?
Oh, okay. Each one is a
detection?
it's F. Yeah. Well, actually, that's throughout the detection process. So F1 through Fn are all the classifiers that we are using. We put them all together to make a cascade of classifiers, and then after that we determine whether or not we have found the object. So it will go through each stage, and then on each stage it determines whether, okay, this classifier is saying that that object is present in the image. If it does say that, it continues to the next stage, and if it doesn't, then it's discarded and you stop the detection. You don't think that it's within this region that you're looking at. So basically, what is a negative image is the image that does not contain the object. So to train actually your own detector, you need to collect many of those images that do not contain that object of interest that you're looking at. So it could be a computer, a box, anything, a human. So you collect many thousands of images of that, usually maybe in the 2,000 to 3,000 could be enough for the purpose of your detector. And then you can get all these images from online data sets. There are many online negative images that you can collect, or even you can do your own video captures. So you can take your camera and go take video of some other stuff and extract all those frames with different backgrounds. Basically, you want to try to look at different backgrounds, look at different illumination, different changes of illumination in different images that do not contain that object. So you don't want to get anything that is close actually to that object in that image. So if my object is some kind of a box, I don't want to get a smaller box or something that looks very close to it in those negative images. So think of something that is way not related to anything that would get you close to that object of interest. And then basically what you do is after you collect all of those images, you put them in one folder, and then you create a text file that includes all the names of those images, which basically is just, you can do that command and have all those images listed in that text box. So for example, that's an example of that. This is an example of the negatives that actually I used to train my detector. So as you can see, I'm trying to do a leg detection, so I don't want any human present in any of those images. I looked at this data set that is being used online, and as you can see, it's just random pictures of things around. There's campus, there's a classroom, outside field, computers, and as you can see, also there are different illumination on those images. So there's darker images, different stuff like that. The more rich your background is, the more different backgrounds that you collect actually works toward a stronger detector. So that's kind of what the negatives are all about. So for the positive, so a positive image is basically the opposite of the negative one. It's just the one that contains the object of interest. So again, you're trying to get thousands of those. Proportion-wise, as we just said, it could be 1 to 2 or something in that range. So, but you want to try to get at least close to 1,000 and above that. So you don't want to train your detector with 10 images. That's the basic idea. So get as close as possible to 1,000, and then you can also add more to that. And basically, you're also going to save all of those in one folder, and also do a text file. But this text file is going to be a little different from the negatives text file, and we'll talk about that a little bit later, because it's not only going to contain the file names, but also is going to contain the marked positions of your object of interest. And that's basically what we're going to talk about in a little bit. So this is just a sample of some of those positives. This is me, yes. Is it?
Why you lost your hat?
What?
Do not include your hat.
Is Chinese Kung Fu, some parts of it. What was the question?
Why you did not include your hat?
I didn't include my head because basically I'm not looking at the head. I'm looking at the lower parts of the body. We have another detector for doing upper parts of the body, which is shoulders and heads and everything else. But for this, it's just we're looking at the lower part of the body. What? Is it? Okay, sure. It's kind of funny to look at it actually right now. Okay, so basically, as you can see, there's the top three. We have some, background that we use. The bottom two, a different background, and actually, I have more images that I use also different backgrounds than this. And it's really good to use those different backgrounds to make your detector more of a general detector, more than I just need to detect for a certain video that I have. Okay, I have one video, I want it to work on that video and only. You can do an awesome detector if you just capture some video that you have and okay, I'm gonna just make it work for this video. It's actually, that's not the purpose of this thing. Yes.
Yeah. You just train your images with just one person in each image for the positive?
Yes, but that's not a necessity. You don't have to have that. You can have more than one instance of the object in the image. So for example, if I had several people walking around and I take pictures of their legs, I can train that as well. And you'll see in the example of when we save all this information to the text file that when we mark those, you can mark several actually objects in an image. So it's not a necessity. You can have certainly more than one, and then you can mark them and tell.
It's just one.
Tell during the training process where they are exactly and how many of them are there.
And another question is that
Sure.
Just for example, it's just for the men or women is separated or is just
It is
someone is scared.
Yeah, my detector is not sexist, so it's not differentiating.
No, just for example, just someone just has a short pants. Just something.
Yes,
like
yes.
that.
Well, there are so many different scenarios that you think of, like if there's a woman wearing a skirt, so
Yeah, or
you don't, or shoes and stuff like that. So of course you can include that to have better
But just
detection.
mark
But when I think about it is that if I'm gonna include those situations, with skirts and stuff, the probability of that detector looking at a lot of things and getting more false positives that it would look at anything that have, like, for example, that shape with those edges and be like, oh, okay, this is a leg, when it's just like maybe a curtain or something like that. There's more the false positive rate I believe would increase tremendously with that. So I wanted to look at as you see in the pictures, okay, that's kind of the stature of the legs, and these are some of the things that you would do with your legs. So
you mean that if you include something like that,
Mhm.
just mark them as this part of the images has, for example, skirt, or for example, had boots, something has sandals or something like that.
Yes. And again, it's kind of looking at for example, the structure a little bit and doing those, for example, saying like maybe that the top right image is a good example. As you can see, like you can
Yeah.
look at those edges and formulate some kind of a template that it would be looking at and match that. So go forward to object marking. As I mentioned before, I kind of found this software. You can actually design your own, but it's always cool to find something and use it, especially if it's a small function that it's much easier to use and faster. So there's a CS team at the University of Utah that they did this small software. Basically what it does is that it opens an image, and it's an OpenCV. It opens an image, and then it looks at the image, and then using a mouse you can, you click, you mark the image, you have this box that you mark your object of interest inside the image, and then you can save that file. It doesn't save the image. You save the information of that, the boundaries of that bounding box, as you see in the example, and save it to the text file with the file name. So it's a much faster process to do, since you're trying to mark thousands of images. Believe me, it's not something easy. Yes.
And another question that why you use the OpenCV? It has a special library for that?
Yes, with OpenCV, there are special functions that actually you can use to train the detector and to create the sample vector, as you will see in the positive sample vector. So with that, with those two functions, it's easier to take those and use it for your trainer rather than doing it from scratch. So that's basically what I did. So as you can see, and this is the first, these are some of the examples. So you see here, raw data is the folder name. Then you have your file name, which is image1.bmp, and then you have this number here, which is 1, that basically is saying there is one object of interest in the image that I have marked, and these are the dimensions of it. So you have 4. So this is you have a box, so it's kind of like just the boundaries of that box that you have there. So that's the bounding box as over there. So basically you get all of these saved into a text file after you finish your marking, but during the training process you need to get rid of the folder name and whatever you have before that. So just rename all of those, and then you will be left with this, and this is the format that should be kept in the positives.txt or whatever you call that. That's the positive images information text file that you want to save all of those in. In case you have two bounding boxes, so you drew two boxes around two objects of interest, then you'll have that number will be 2, and then you'll have 4, and then space, and then another 4. So the first 4 numbers are for one of the two boxes, and the other one's for the other. So it doesn't matter which one comes first; it matters where they are. So and this is exactly what I did. Is, for example, so I have that image, and actually I cut a lot from the outside. There's more to it. But yeah, so that I drew a bounding box like that, and then you hit space to save it, and then enter to go to the next frame. So what I did in my training process is that when I collected my positives, I took a video of myself, walking around, and I took all those frames and I just looked at marking them, each frame, and saving all this information to the text line.
OpenCV, they already have like those training, standard training set that help you to train so I remember they have the upper body, right?
Yes, with OpenCV, exactly. With OpenCV, they have several default cascades that you can use by default. So there's the face, there's upper body, there's full body, and some other stuff. Huh? No, it's an already trained cascade, so it's a cascade that you can use. So it's a .xml files that they
I
have.
love that you use OpenCV.
So you can either use that or you can train your own detector. So yes, they do have those
So
ones.
do they have lower body?
I don't think they have lower body. They have maybe they do have lower body. I know for sure they have upper body, they have full body, they have face detection. I doubt they have lower body. I don't remember. Did you see lower?
I didn't check.
Okay.
And you can add something.
Certainly, you can add. You can. You don't have to do human something, but the ones that they have are all human related. The face, upper body, full body.
No, for the face, you can add some pictures that
Yes, you can.
train.
You can train your own
add-
detector, and you can compare it with the
that
ones
one.
that they have. Yeah, the one that they have for the face is really good. It's really good. Works really well with real time. You can just have a webcam run real time and use their face detection. It's really good. Basically, this is one of the attractive stuff about doing this kind of a detector using OpenCV is to have it run in real time. So yeah.
How about this? Really good, saying the frontal face?
Yeah, but when it comes to rotations, it's a little, it gets a little shaky. But there, actually, I read a paper about some people that did another face detection using the same methodology, but with much more positives that different rotations, and it performed a little better than the other one. So and another thing is over here is that you see that the legs are rotating, and we have so many different positions that we took, and you'll see in the some of the results is that some of those legs are just like this way and that way, and it was still actually detecting them. So rotation is an issue with
And
the hardware.
upper body, is that only frontal or like how do you
I'm not sure. I didn't actually go too much in details about that, but I know that it's not immune to rotations. The ones that they had, the default ones that they had, are not very immune to rotations. So I'm not sure if it's frontal, back, or sideways. We can run it maybe afterwards and see how it performs. Okay. So you have to create what is called a vector that you use actually in your training set. And to do that, there's a function with OpenCV that you can use. It's called create samples. And basically what you feed into it is some of the stuff that we've been preparing to this point. So we've been doing a lot of data preparations on the positives, the negatives, and everything. So what you do is that you take all those positives, for example, I save them in a folder called positives for me because that's much easier to remember. So it's in a folder called positives. and it's a positives.txt is the text file as we mentioned just earlier, the one that after we did all the markings and we put the name of the file, don't sleep, and how many objects of interest are found in the image, and the boundaries of the bounding box, and then the data/positives.vac, that's where the file where we want to save the file at, so that's a directory for that. And then you have the num here, that's the number of samples that are being used for this vector. And you'll see in a little bit that I used actually, I did 890, I did 1,890, and then 2,890 positive samples to train 3 different detectors and see, actually, compare what kind of detection rate I get and how good of a detector will I get by increasing the number of positives. And then you have the width and height of the rescaled image, because it kind of like rescales it, and that's kind of what you're looking here about. For example, the 20 by 20 is kind of like the smallest or the minimum size that actually this detector would be finding that object of interest. So usually you don't expect, in general, you do not expect your detector to find, for example, legs that are smaller than that. And that's pretty small if you think about it in a big image. Let's say 640 by 480, it's a big image when it comes to legs. It's usually bigger than 20 by 20. So when you go really far away, it's not, your chances of detecting legs just goes down very, very bad. It goes really fast down. So
It's the minimum.
you can think of it kind of the minimum. It's not a defined minimum, but you don't expect your detector to detect less than that. But what it does is that it rescales the ones that you have already marked and the ones that you already have as positives. So it rescales them and uses them like that. Okay. Yeah. So next to the training example here. So basically, again, this is the Haar training, and that's basically what we're doing today. That's another function in OpenCV that you can use and feed it all the stuff that you have till this point, which basically is, again, the positives. And here, again, you add the negatives, of course, and you have your positives vector. And then you can even assign a number of stages that you would like your detector to go through. So how many stages of classifiers that you would like it to go through before it determines with a certain percentage a good detection rate or not. And then you have your memory usage, so you can use, for example, I assigned 1 gigabyte of RAM, for example, to be used during this training process. So you can assign that on your PC or something, because the training process usually takes a long time. Sometimes it takes several hours, sometimes even more. All depends on how many samples you have, what you're feeding it, how many features you're looking at, and some other things. So the more you put in it, of course, you're going to have a longer time to do all the computation, to do all the training. Again, the number of positives in this example is 2890. The number of negatives is 2977. So it's not actually 1 to 2, but because actually I trained my first detector, it was 890. So my negatives were way higher than that number. And then when I did the 1890, I just forgot about whether I should add negatives or not. I just went with it, and then I added another 1,000, and it was 2890, and I just left the negatives as is. Yes.
Yeah, for your positive part, you just feed that part with the detected legs, or
Mhm.
just the images with the
It
legs.
will take
said that
the image
this
file,
part-
and it will take that part. So you're looking at that part, saying, okay, this is my object of interest, and that's basically what it needs to
for
know.
training.
For training, of course, yeah. Otherwise, it doesn't need training. If you,
Yeah.
that's the main
Yeah,
idea.
because
of it,
you
so.
just for the positive, you just detect. You have to feed them with the detected
Yes.
legs.
So you feed them with as many samples that you have of the object of interest with different backgrounds, so it would have an idea on the edges that it's looking at and where kind of it would think this object is. And then as you give it new test images, the test images that you didn't, of course, train it
Yeah.
with, so it's
Just
silly to do that. So it will make an assumption and give you a certain detection rate on that. Sure. That's basically, you do this, and after you hit enter on this command, just do not expect it to finish in 5 minutes. It's gonna take, I think it took me on the 2890, it took me like 4 hours or something like that on the desktop over there, which is pretty decent desktop. It's not slow at all. But on the 890, I think it took like 2.5 hours or something like that. So the margin was not really increased by that much when I went over 2,000 for another 2,000 samples on the trainer. So basically, after you do that, what happens is after you do this whole training process, it takes it saves all that information of the. It creates that cascade, and it actually saves several folders of all the stages that it went through, and how the cascade reacted with all different stages, and then it creates a .xml file, which basically is the same as the default ones that OpenCV have, and basically that's the one that you're gonna use when you're doing your detection. So it kind of all rounds back up, and your result is that .xml file that you use in your code. The testing process, you want to, of course, use some images from online datasets or even video capture. So you can go online and just Google, for example, human, give you all kind of absurd stuff that you can just use and see what kind of detection you have. And then, or you can do a video capture, as we have done on several occasions, to just collect your own video. And that actually, to me, is more interesting than some online dataset, which usually is, for example, oh, this is specific for human detection. You know, even though that is decent, but I would always prefer to take so many different video captures of people in different scenarios, different backgrounds, so I would know how really good my detector is. Otherwise, I don't want to just use something that works only in one situation. So, of course, you're not going to use any of the images that you used for training. That's absurd. Again, that's really silly, because that doesn't make sense. It's okay, detect, I trained you on this, detect it, well, else you can detect it. Test on different scenarios, as I said, different backgrounds, and check if further training is required. So sometimes you might use different samples. Sometimes you might decrease the negatives or the positives. You'll have different results. Sometimes changing the backgrounds that you used on your negatives or the backgrounds that you used on your positives also have a lot of effect on that as well. So to me, having one way to just go with, for this hard training purpose, just thinking of one way to just have the most optimized detector, the best detector of anything else, just really difficult to think of, because you can change so many parameters and have so many different results for different test images that you bring in.
One question.
Yes.
The percentage of the training in the training set is the 100%, or you have some miss data in the training set?
No, you have some actually missed. So there's a certain percentage that you want to reach before you decide it's enough for actually different stages. So if it does not meet that requirement, that threshold, it does not take it. So it has to look at that. It's not 100%. It's not that. Okay, so back to my great leg detector. As I mentioned before, I trained 3 detectors on 3 different positive samples, 890, 1890, and 2890. And then I did my testing on the INRIA dataset, which is basically an online dataset that is really famous for human detection and everything. But it's actually used for full-body human detection. But I just, I wanted to look at it and see if because legs are parts of humans, so it should find it. And also I did a small video capture right here in the lab, an indoor environment. It's still, I want to do more testing actually on things outside the lab, because I did my training kind of inside the lab, even though it's a different background, because as you will see, it's a different background from the training ones, but still, I would like to actually do more testing outside. And I was not wearing the same pants, so as you will see in the detection. So this is from the INRIA data set. So I have different examples here that you can look at and see. You kind of evaluate maybe some of those stuff. So you can see on the first two, it's detected. It's great. Okay, it can look at the legs. See on the third one, it gives you just some two round circles up there on the upper left of the image, which of course those are called false positives because it has not detected the legs. It's just detected something that thinks it's the legs, but it's actually not. So this is due to some just false positive rate of the detector. It's not working that well on that image.
Is there any statistics on the accuracy?
Yes, we will get to it in a minute. So, and then you see the image on the bottom left. You see, okay, you have detected legs over there, but you also detected some false positive. I don't know if you can see that.
Yeah.
Okay. And then there's, of course, those images that you detect absolutely nothing, but actually your object is right there. So that was for the 1890. This is the 1890 did actually a little better. I don't know why I'm showing different images. Probably I should have showed the same images. I think some of them here are the same, but not all. But there are so many different scenarios that actually, to me, are really interesting. So, for example, the first one on the top left, you see that it draws two circles around that area, which is interesting because there are two humans over there, so we know that there are two legs, but I don't think that it's thinking that. It's actually looking at those two regions, and then at each region it's just giving some detection, thinking that those are another two legs. Yes. Could be, I'm not sure, but for some reason that works really good. It's like, oh yeah, there are two pairs of legs in there, but I don't think the detector is that smart. When we look at it subjectively, it's like that. And then of course there's some false positives up there. Second image is working really well, but those two guys, there's a guy way in the back over there. He's kind of occluded a little bit, and the guy on the left right here, who is also not detected, there's a little bit of occlusion. That could be the reason why it's not detected, or it's just the detector couldn't find it in that image.
Excuse me. How
Sure.
do you do for example, if you for the top right that you didn't find any legs there, you can just that picture or something like that, which was for training, is a positive. Yeah. And for example,
okay.
for the others, something in the second picture, you just detect something is not leg. But you can do something like that for the
a negative. Sure. That's an idea. We can try that. I don't know how much it would affect
How you
the
can
set or not. But then if I'm gonna use these images in the training, I'm not using them in the testing. But that's
something
okay.
like
No, that's
that.
certainly sure. If we're looking at some things that it's looking at and thinks it's what we need and it's not, we can do it as a negative. Maybe that would increase the detection rate. That is that might be true. And then again, it might not. So it's really variable situation.
I mean that, for example, for the positive, you can just add something for positive images. But for the negative part, I think it's hard. Maybe you can just remove something
you need to
from
remove
the database. Something that train database.
And then again, if you're doing your own video capture, so you're looking at some background and some people walking around, you can also take, some pictures of that background without the persons as well. But again, if I'm gonna do that, I want to do that. Okay, I'll put it in, but I'm not gonna use it in the testing process. I want to use a way different new background up there. So, how would it work with that new background, with that new situation? We're not sure. So this is kind of like the process with the hard training, is that you're trying to get kind of a best option, which basically is not the best all the time. And then on the bottom two, it's just detecting those two. And then with a little bit of rotation on the bottom right one, he's not actually standing straight ahead. And of course, there's another guy who's over there who's turning around. But With legs, it's a little different than face or upper body, because it's not that different from if you look at that person from this side or from the back, it's almost the same. So it's not that much difference. So the sides and the rotations are important as well. So, interesting enough, when I increased another 1,000 positive samples, you see on the image way in the middle over there, upper middle, that's actually the same image over here that it did not detect it, and then it did detect it over here for some reason. And it's again, so you're looking at this circle that it's not circling the whole area of the legs, so it's just maybe some parts of the thigh, for a better word. And then, but it found something in that area that, again, it's kind of a detection, but it's what no, it's okay. And then the first image as well, there's some other false positives, and there's this image on the right that's also a little interesting that detected one pair of legs. It didn't detect the other two, but with a little bit of rotation on the other two, did some false positives. On the lower left side, it detected the legs and with some other false positives, and then it detected that area twice rather than one time as well. On here, it's a little interesting. On the lower right, is it found the father, didn't find the kids, which again could as you mentioned, there are a lot of things that if you're wearing a skirt, I doubt that it would detect it. If you're wearing a mini skirt, it might detect it because you see on the lower left, some of the legs are covered, with one piece of cloth, which is the coat, and then the other is left out. But you can. I didn't test it on skirts, but of course you can always have some ways that you can trick the system. Of course, we're not. It's not that smart. It's as smart as you train it in the ways that you do train it. So on 50 images of the INRIA dataset, as Bailey wanted to see, so bad is that these are the detection rates. It's on the first one it was pretty bad. 54% that's really low. It's nothing that you wanna actually use to do that. But on the 1890 it become average. It's okay. It's 72%, then 74% on the 2890. From those, actually, it's to me overall it's bad. It's not something that I would use for I don't know why on those 50 images from the INRIA I didn't actually detect it that well, but they had different backgrounds, they had different rotations and everything.
What's the false positive?
Yeah, the false positives is when you, as you see in this image, on the let's go with the bottom left here. See that blue small circle over the human up there? So that's a false positive because that's not my object of interest. My object of interest are the legs. So when it finds something else, that's a false positive. And it finds it, not only finds it and says like, that's pointing that, okay, I think these are legs and those are not. So the false positive, kept on increasing while I increased the positive training samples, which is interesting, but with that is,
The detection rate is true positive, is it?
yes. This is, the detection rate is when you find the legs.
So when you increase the true positive and the false positive increase even faster.
Yes, yeah. You mean like percentage-wise?
Yeah.
It's comparable. It's comparable.
Yeah, your data, your
Yeah.
positive data has overlap, for example.
Oh, no. The false positives, again, okay, so for example, I have, I don't want to write on. So, in this image, for example, here, again, let's look at the bottom left over here. So over here, I would say on this image, okay, I have detected the legs for this image, and also I have a false positive. So I count one false positive and one leg detection. See, so some of the images over here, for example, on the left top, you see the left top one? So I have two detections and I have two false positives. I count both of those. See, I don't count only one. I count all the false positives in that image. And that's why you see the false positive rate is actually really high, but it shouldn't be that high. Because in that case, I don't just say, okay, I have a false positive, that's one. Yeah. That's one thing. The other thing is that we're looking only on 50 test images, which usually when you do your test images, you want to look at 200 or more images. So I believe that when you increase that, you're looking at different things. You might have a better detection rate and maybe a decent false positive rate. So, but I cannot just make that analogy and say, oh, okay, yeah, it's going to work that way. I just looked at 50 images. I should have maybe looked at more, but I didn't. But on 50 images, that's okay. I mean, 72% on 50 images, look at what, 40 some, 30 some, maybe close to 40 images found that I found a human in them. That's okay. It's not bad. When you're looking on like 200, 300, even more, the detection rate would probably increase. I don't want to say that because
Right.
it depends on the images. It depends
you
on
really need to test that first and see if it generalizes. 50 is probably not really a big number.
Yes, but yeah, when I did actually my test images for the other detector, I used like 800. But anyway, yes, certainly for this approach, there should be more test images involved in this, and it's just that I think when I took that video in the lab, and you'll see in a little bit, I took 50 frames of it. So that's why I just said, okay, I'll take another 50 from the INRIA and just do that. But
So
yes.
For training, the training sample was from your video, or the training sample was from different place.
The positives,
You use for training.
yes, the negatives or the positives. The negatives, the ones that do not
positives.
have positives, not from my own.
From your own.
Yes, exactly, and that's what I'm saying. I mean, it's okay because I use my own
Yeah.
positives, all of them from that.
It can
So-
be different for the test set because
Mhm.
they look actually different from your training set.
Exactly.
So
Yeah.
how many samples do they have in this INRIA?
There's you mean positive ones?
Yes.
I didn't want to actually use any of those in my trainer
Yeah.
because I wanted to keep those as tests. But we have like 1,000, 1,000 some. Yeah. No. But yes. If we take more with different backgrounds, I believe it would increase that detection rate by a lot.
I guess if there are many of them, maybe you can divide part of for training, another part for testing.
Mm-hmm.
Is that enough?
Yeah. I just didn't want to use any of those in my training process, but probably I should. That would increase the detection rate. Because I didn't use too many different backgrounds. That's one thing.
It's more diverse.
And it's more diverse. It's looking at different legs, different sizes, maybe different stuff. But for it to work in that sense, to me, is like, okay, that's not bad. Need to work more on the training process and include more positive samples that have much way different backgrounds and different scales and stuff. So.
Okay, one question about the training.
Okay.
For example, the last row, all of the data is new, or you add only 1,000 training sample to the.
Yeah, basically most of the training setup is exactly almost the same. It's very identical. You go through the same steps. I just included more positive samples and
You
then I
add
did
only-
marking.
Yeah, it means, for example, it's not maybe 6,000 sample that you test, for example, for 1,000 and 2,000 and 3,000. It's not 6,000. It's only 3,000 positive sample. It's okay.
Oh yes. So I
think
increased
because-
that. Yeah.
I think because of this you have false positive rates increasing
Okay.
because you add some data that is not, for example, new. It's the same data,
Mm-hmm.
and for example, in the
Overlap.
last one you have 2,000 old one and
Mhm.
only add 1,000 and.
That's true for some part of it because actually when I added the other thousands on both of those, I used the what was there already, and then I added some more from a different background, but of my legs. So yes, I understand that. So,
Did you check, for example, for each 1,000 separately, for example, for first 1,000, second 1,000, and third 1,000 training, and find the false positive and detection rates?
oh, okay, I see what you're saying. So
Because
do
you
separate on all three,
Yeah.
and then do combine.
Because after, if, for example, in one set, if you have a better detection, it's good to add. But if in
Mhm.
one set you don't have any
Certainly.
improvement, adding more data is not help you to.
Exactly, and that's basically with the hard training. Sometimes you reach a point that you think, okay, I'm gonna put like 10,000 positive samples, and I think that's gonna be working perfect. That's not the case. As you mentioned, some of those, if you're adding more of the same, then it's not really helping that much. But also it's shooting up some of the maybe the false positive rate, or taking maybe even the detector could get really confused at some point and be looking at stuff and just I actually expected the false positives to increase with the detection rate for this training process because of that, and because the detector now is maybe more sensitive. It's gonna like be working a little harder with what it has been trained so far. So yes, certainly we can try to do each 1,000 on its
I
own,
think
then combine
it was
it.
better that first you test on each of the, for example, new data,
Mhm.
and after that decide about adding or not.
Yep. Yes. True. Actually, it'd be really interesting to actually do that and separate those and see how each react with the training.
Yeah, and a question.
Uh-huh.
Yeah, your methods depend on the size of the legs in the pictures or not. For example, in the family.
Yeah. So it actually it doesn't to a certain degree, because what it does is that actually it takes all those marked and it rescales them, and then it looks at a minimum of, as we said, kind of 20 by 20. So it's not gonna look at things that are smaller than that. It's the legs that are smaller than that. It's probably not gonna detect them.
Even in the one image, maybe has the
Big legs and then
big
small
and the
legs.
small legs,
It depends on how small the other legs are. And another thing, and this image
Right.
also is like, on the kid on the holding his father's hand, I guess. You see, it's not only small, but it's also maybe it's not that obvious that those are legs,
Yeah, I
because
think
it's
so.
like kind of like together and yeah.
because of the
I can't just say whatever here and be like, oh, it's because of that, because actually I'm not sure. It's the
but it can detect
how good the detector
scale.
just found it. Yeah.
But it can detect the scale of the leg.
Yeah. It can detect different scales, and you see the images actually they're not all the same. Legs. There are some bigger
Oh,
legs
yeah.
and smaller legs. So this is actually close on the top left.
Yeah.
The other ones are a little
Top.
further, and
Yeah.
you can see in the same
Yeah.
image.
The top.
Someone is way behind.
Thank you.
So here's what Anusha was laughing at. This is me, and that's the restroom. For some reason, I after I took that and I started doing the testing, I'm like, interesting. When I like adding those pictures, it's like, why is there so this was interesting to me. I again took 50 frames through a video capture. It was a fast video capture, and I tried my detector on it. I don't think it was because of me personally, because I had different pants, and I gained weight since then, and I guess the legs didn't gain too much weight, but it actually did really much better than in the other cases. It could be because of the background, could be because of some other stuff, I'm not sure. But the detection rate went up to 92%, and the false positive was still decent in a 16%, which you want to actually decrease that to 1% or even less. You don't want to have false positive. You want to actually put it at 0. But
What did you use for training in this particular?
it's the same. It's the same detector that did the 74% and 34% on the INRIA. So here's the other thing. If when you change your test images, you have the different results. So it depends on. Here maybe it's I don't know I'm using frames of a video sequence. So it's kind of like this. If it's gonna detect the first frame, there's a really high chance that it's going to detect it in the next frame. So as I go, actually, I'm walking around, even though it's different rotations and stuff. But for example, on the lower two, it's close. It should detect it. If it detected the first time with a certain, confidence, it's gonna detect it the next time. So with a video sequence that you have, all those images are almost the same, and you're just like walking around. It's gonna find it somehow. But also I'm interested in looking at different positions of the legs and different rotations and stuff like that, which it reacted really well in this situation compared to the other situation. So basically today we kind of went through a recap of Haar. We kind of did a step-by-step on the training process. You actually can take this and even try your own, do detection of a pen, the detection of a computer, do your own detector, and if you need any help, I can actually assist on that. It's really interesting to play around with this a little bit if you have free time. No one has free time anymore. Create samples running the trainer testing, and I showed some of the results that I had, and then just some famous people that I need to always reference to and include over here. Actually, this is the other detector that I adopted, and I changed the parameters that it has, and we tried this algorithm. And this is the histogram of gradients approach, and this is looking at a full body detector, human detection. And yeah, you see that it was dancing all the time, going back and forth. It did actually an awesome detection rate. I think it was like 94% on this video frame of both of you, because here like it has two, and this is not, again, this is not Haar. This is histogram of oriented gradients approach, and I changed the parameters and I did some more testing on them, and this is one video capture. Yeah, I took the OpenCV and I changed some of them. Yeah, the HOG descriptor in OpenCV.
Do you train it, or you just use the
I use the default ones. I use the default parameter, the default OpenCV HOG algorithm, and then I changed some of the thresholds and some of the other parameters to see what kind of different results I get on those videos. Again, CW was dancing all the way back and forth, and so did Salmon at the end. I have more funny pictures, but it's too much. I had over 600 frames of this, and actually the other detector is much better than the Haar one. It has a much better detection rate, and it did even better with those people. Which to me it's just a lot. It's really interesting on some of those cases I put out there. It's like there's some occlusion up there on the upper image. You see Amin is occluded a little bit by Schwang, but still was able to detect Amin as he moved out. Actually, like two or three frames before that, it didn't see Amin, even though you can see his head and maybe his leg, but it didn't find that there's a human there other than Schwang. So at some point it was like, and the other cool one is that down there, you see Nafisa is way back, and she's a little included by Amin right there, and it was still able to detect Nafisa way there in the background. And here's another cool Schwang is really happy. Nafisa was celebrating, she just said it's too much. She was way out, and yeah. And you see Amin is really happy, so it's Farnaz and Schwang. And Li Jun missed her chance to become really famous. But yeah, maybe some other time if I do another presentation, we'll go more in details about the histogram of oriented gradients, and we'll show some of those results. And
me and Bay are missing.
who are you? So that's basically what I have for today. If you have any other questions, I'll be more than happy to answer them.
Can you back to the slide number 4?
Oh, okay.
And what is the reason to select this Haar features? Do you have
So basically you're kind of doing something close to like doing edge detection. So you're looking at some features. You have things that have that orientation of the edges, and then you have the fronts.
For for example, for the leg or body, maybe you have some shape. I don't know, maybe triangle, something like this. That it shows the some part of the body, for example, shoulder. And it seems if you add some hard feature like the triangle, it can help you to.
Yeah, and more of those actually are visited. Not only those are just some simple examples of them. But you have 2 region, 3, 4, even 2, 3, and 4 regions of Haar-like features that you can use, and it does to go around and see what kind of orientation at different points it's doing. So these are just some simple example of that. But Dex kind of like uses this approach to do the training.
And another question, is there any method, I mean that is not training for the detection, for the detection method, is there any method just you use the training set?
You can use that?
Yeah, I mean that, for example, you just use the training set for the detect of the legs or body.
Okay.
Is there any method that they doesn't need to training set for the for detect?
Is there any heuristic method that does not need to
Training set.
training data?
You mean just a detector that? Actually, there are. The one that we just visited is just you train your own detector and what so. But some of them, some actually other approaches, it's just you look at some other things that you don't actually need to train offline and do your detector and then use it during your testing process.
How accurate it? How accurate it? That method.
I don't
is
know.
better than this
I didn't
one?
look too much into those ones. Seems like maybe Billy.
No, I guess it's kind of difficult without training.
Without
so.
training it's a little difficult, but I believe there are some approaches out there that.
It is, but this one.